Hello and welcome to Mostly Climate. I'm Doug McNeall and today we'll be talking about climate tipping points. The phrase tipping point was popularised by Malcolm Gladwell, whose book in the year 2000 explained how in social systems, spreading ideas, messages, behaviours and products, small changes can make a big difference. Climate tipping points are thresholds in the Earth systems or processes where the system can change suddenly, dramatically and even irreversibly due to even a small nudge. Joining me to explore this fascinating concept and to learn how close we are here on Earth to witnessing climate tipping points is Professor Tim Lenton. Tim's head of the Global Systems Institute at the University of Exeter. He's a specialist on tipping elements in the Earth system. Hi, Tim.
Hi, Doug. Thanks for having me on.
You've worked for many years on tipping points and you've been instrumental in warning the public and policymakers about the dangers of crossing dangerous thresholds in the Earth system. So how and why did you come to research climate tipping points in the first place?
Well, as a student of the Earth as a system, I was kind of well aware that we're only here breathing an oxygen-rich atmosphere with a fairly stable long-term climate, thanks to the Earth having gone through some past tipping points. And as I'd been studying the contemporary Earth system along with everybody else through the 1990s, it became increasingly clear that we could risk tipping them in the near future. And I felt at the time, as a scientific community, we weren't putting enough attention on those events. They were high impact events in everybody's books. So many of my colleagues thought they were very low probability events, but in any sane risk assessment, you still have to look at the high impact, low probability events and try and get a better grip on their probability and impacts. So that's what motivated me, and I worked with John Schellnhuber really on this from the early 2000s onwards.
And you've been looking at the Earth as a system, is that right, rather than any of the individual tipping points, or have you been looking at the individual tipping points as well?
I've tried to do both, Doug, but I am a student of Gaia, of James Lovelock, really, and his way of thinking, which I believe really first gave us a coherent concept of the Earth as an interconnected system. But just like any complex system, you can divide it into subsystems, and those subsystems interact, and that's true of the climate system. What I was really interested in was not just speculating on or thinking about, is there some global tipping point? What about tipping points in subsystems? And if they can happen, shouldn't we give those subsystems a name? And that's where John and I came up with the name tipping elements for the bits of the climate system that could pass a tipping point.
So could you describe the difference between a tipping element and the tipping point itself?
So the tipping element is the bit of the climate system that could pass a tipping point. But the tipping point is a description of that point in time and in space where a small change makes a big difference to that subsystem, that tipping element.
There's another couple of concepts that I'd really like to get across. The idea of a feedback, a feedback in a system, that's really important, and also to irreversibility.
Yeah, so feedback is an absolutely crucial notion, and it's where you have a closed loop of causality, we would say, within a system. So some change, like a change in temperature, causes some other changes within the climate that may feed back and either amplify the initial temperature change, which we call positive feedback, just in the mathematical sense of positive, or they might damp the original change, counteract it, and then we call that negative feedback. The climate system is riddled with feedbacks, just like any complex system. What's crucial to tipping points is that the positive feedbacks have got really strong and they've ruling the roost, if you like, for a while. So normality for most systems is that we recognize they have a stable state or configuration, like the ice sheet's there, it was there yesterday, it was there 100 years ago. And stable states are maintained by the damping or negative feedbacks. And when it gets changed to the point that the positive feedbacks get really strong, that's where a tipping point can happen.
You get a runaway effect, I guess, where a system, once it's been tipped over this threshold, will run away with itself.
So, I mean, it's really important also to realize that positive feedbacks don't always run away. So let's say I start with 1 degree of temperature change. I could go around a positive feedback loop once and get back an extra 0.1 degree of temperature change. So that'd be amplifying. But if I went around the next time, I'd get back another 0.01. I'll go around again 0.001 and so on. That's a positive feedback, but it's not running away. But if that feedback gets stronger and 1 degree of warming causes a response that adds another degree of warming, which goes round again and adds another degree, then we're at the runaway threshold.
And how about irreversibility? So there's this idea that you may cross a threshold, and that once you cross that threshold, the behavior is changed for good, or the state of the system is changed for good. And hysteresis as well. I understand hysteresis is a similar concept.
So if listeners can picture this in their head, try to picture 2 valleys with a hill in between them. Those 2 valleys represent what we call alternative stable states of some system. You can only be in one state at one time. And maybe we think of which state we're in as being marked by a ball rolling around in whichever valley you've chosen. But, you know, the world can change. The height of the hill between the 2 valleys can drop, and that makes it more and more likely that the ball might roll off into the other valley. That's the so-called tipping point. Once it has rolled off into the other valley, it's not easy to get back. And that's what we mean by irreversibility. We don't really mean it's never ever going to be possible to get it back always, but it means it's hard to get it back, and we might have to change the system a lot to get it back, and we'll get it back at a different place in terms of, say, global temperature to where we tipped it over in the first place. And when that happens, that's what we give this fancy mathematical language of hysteresis to. We say, well, we call it path dependency. You know, going from A to B, we went along one path, but to get back from B to A, we had to sort of shove the system a lot to a different point to come back.
Okay, Tim, so there's quite a long list of potential tipping elements in the Earth system, and some of them seem like they're riskier than others. Some of them have got bigger impacts than others. And some of them are sort of more probable than others. So what are the biggest risks? What are the systems that we should be really paying attention to?
Well, let's start just by breaking it up into 3 categories. So there are tipping points in icy bits of the climate system. So the tipping elements there are like the West Antarctic ice sheet, the Greenland ice sheet, the Arctic sea ice, the frozen permafrost soils. Then a second category, changes in the circulation of the ocean or atmosphere or bits of it. So we've got the great overturning circulation of the Atlantic Ocean. We've got monsoon systems, a kind of atmospheric circulation. And our third category is some bits of the biosphere, like the Amazon rainforest, the boreal forests, and arguably the tropical coral reefs. Now, out of all of those, which ones keep me awake at night the most? Well, actually, if we started to see severe disruption of monsoon systems, because they could change fast and many hundreds of millions of people are usually depending upon them, particularly in West Africa and Indian subcontinent. But in terms of evidence of change that's happening, the biggest alarm bells are ringing in West Antarctica, where we see physical evidence consistent with possibly having passed the tipping point for irreversible retreat of part of the ice sheet that drains over a metre of sea level rise. So it's collapsing slowly if it's collapsing now, but the more we warm it up, the faster it collapses, and that one would be very hard to reverse.
And that sounds like something that's quite a long time scale, or is that on a shorter time scale? Are we talking human lifetime, or are we talking multi-century?
In general, with ice sheets, we're talking about several centuries to collapse the ice sheet. But of course, the nature of tipping points is that they are self-accelerating. So one should not be too guided by how fast or how slowly the ice is collapsing and the sea level is rising right at the moment, because the point is it's accelerating. But yeah, in the worst case scenario, we'd still be talking about centuries to, say, lose the West Antarctic ice sheet, which all told is about 3.5 meters of sea level rise. But I wouldn't take too much comfort from that, because obviously that implies accelerating rates of sea level rise on the way there. That's already posing adaptation challenges if you live in a small island state, and the faster the sea level goes up, the bigger those challenges. extraordinary thing about the climate. Different bits of it have different intrinsic timescales, and somewhere in the middle would be the threat to collapse or trigger the dieback of, say, large parts of the Amazon rainforest, which would be a tragedy on so many levels, particularly as the crucible of biodiversity.
Absolutely. And I think we'll come back to the Amazon rainforest later. We've got a great interview with a Brazilian scientist that we'll listen to. I guess I'd like to talk a little bit about perhaps where I came in with the research for my PhD back in 2004 was the Atlantic meridional overturning circulation. And it was very popular at the time. It popularized the idea of tipping points, apart from Gladwell's book, because of this film, The Day After Tomorrow. Have you seen The Day After Tomorrow?
I have some time ago. I chuckled as the storms run the wrong way round in the film. It's certainly science fiction rather than science fact. But like you, many of us got into thinking about tipping points because of this poster child example. And the observations now are showing us that the overturning circulation in the Atlantic has weakened about 15% since the middle of last century. And we honestly don't know if that's just within the bounds of natural variability or if it's the beginning of the end. Let's hope it's not the latter, because we know it's an amazing connector of things in the climate system. And the Earth's recent past climate record shows us that if you break that overturning circulation, you're going to disrupt the monsoons all the way around the planet, including in India.
So we know that this overturning circulation brings heat from the low latitudes up towards the mid latitudes and towards the poles. And we've actually got an interview here with Dr. Richard Wood, who's the head of Climate, Cryosphere and Oceans Group at the Met Office, who helps to take us through this great big conveyor belt of water, salt and heat that's so important for local and global climate.
There's a system of currents in the Atlantic Ocean, which we call the Amok for short. It's a current system that actually spans the whole world. Essentially, it's driven by warm water coming up in the North Atlantic to northern latitudes where it loses heat to the atmosphere. As the water loses heat, it cools, so it gets denser and sinks down to several kilometres below the surface of the ocean, and then it flows back to the south. It spans the whole of the Atlantic Ocean, and actually it has tentacles that go out into the global ocean as well.
So this great interaction between Amok and the climate is this two-way process where the climate changes can also alter the behaviour of the oceans as well as the oceans altering the behaviour of the climate.
The Amok is really driven by the density of the water. So this warm water gets cold and sinks. But another factor that affects the density of seawater is salinity. So that's the amount of salt that's in a package of seawater. So if we were to add fresh water to the ocean, so for example, from melting glaciers or just fresh water from precipitation falling on the surface, that tends to make the water fresher, and that's less dense. And so that would tend to reduce the amount of sinking and hence weaken the circulation.
So if climate change can bring changes to the Amok, how far might those changes go?
Because the Amok is a circulation that spans the whole globe effectively, it's a fundamental part of our climate system. We don't think a collapse is imminent in the next decade, say, but it's a possibility that we need to keep aware of. Climate models suggest that over the 21st century, the Amok will weaken as greenhouse gases increase. The weakening of the Amok gives us a cooling effect around the North Atlantic, so that would actually delay some of the effects of global warming in the regions around the North Atlantic. But as greenhouse gases become stabilised, we would need to do to stabilise global climate, the Amok in many models starts to recover. So that gives you a kind of delayed warming effect. So effectively the Amok is delaying the warming that we see in the countries around the North Atlantic. But eventually, if we stabilise climate, that warming will eventually come back to bite us.
So Tim, I think this is really interesting because we've seen that you have this suppression of warming and the North Atlantic hasn't warmed as much as it could have done due to global warming. You know, other places have warmed more. And I find it fascinating that we might just be delaying some of that warming that's occurred.
Yeah, and we shouldn't take any comfort from the thought that an Amok collapse might counterbalance the global warming signal where we live in the UK, because as the Met Office's own models show, it'll be a whole lot more seasonal climate with some very severe winters if we do collapse the Amok. And the storms coming rattling across Ireland and the UK are like nothing you've seen before, as far as I can see in the model. So yeah, the problem is it changes the world in an interconnected way, and it will cause phenomenal potential damage in the monsoon regions around the tropics. And interestingly, it leads to the sea level height readjusting and potentially up to a metre rise in sea levels around parts of Europe, for example. So it's got all sorts of effects, many of them detrimental. And when we modelled what it would do, an Amok collapse, to land use and agriculture in the UK, essentially, because it gets a lot drier, it eliminates arable farming from the UK. Now, that will be the least of our worries if an Amok collapse happens, but it just serves to illustrate how it would basically change the face of the world.
So that would definitely be classed as a low probability event, wouldn't it?
Yeah.
But still, some of those impacts would be felt with a smoother reduction.
Well, they would, but also, I mean, you and I, Doug, are sort of professional modelers, but I certainly don't pretend to fully trust the models I use. I don't believe that they are reality. And there are other sources of evidence to suggest our models may be biased too stable for the Amok, lean towards it being less stable than the models think it is.
Okay, let's head north of the Atlantic and to climate scientist Dr. Ed Blockley. So Ed leads the Polar Climate Group here at the Met Office, and here he is introducing the Arctic and why it's important for our climate.
The Arctic is much colder than the tropics, and so we have a very strong temperature gradient, and this controls atmospheric circulation in the northern hemisphere, such as the jet stream. With warming in the Arctic and reduction in sea ice, this temperature gradient is being reduced, and so there are potential implications for the atmospheric circulation and for the jet stream. Sea ice decline can have an impact on other large-scale systems, such as coastal permafrost erosion, and often sea ice forms stuck to the coast. It's known as landfast ice, where it protects the coastline from the warmer ocean.
The Arctic plays an important role in regulating climate, and in particular, Arctic sea ice. However, interpreting sea ice levels is not straightforward.
One problem that we have with understanding the decline in sea ice is that actually the decline is very small compared to the seasonal cycle. For example, we had 3.75 million square kilometres of ice extent in September last year, and then we come to the maximum in March, which is just under 15 million. We lose a lot through the summer and we gain a lot through the winter anyway. And any one particular year we wouldn't really attribute very much to. It's all about the sustained long-term decline. We have seen a sustained long-term decline in Arctic sea ice cover over the last 4 decades. On average, this equates to losing around 87,000 square kilometres of sea ice extent each year, an area more than 4 times the size of Wales.
As seasonal changes to sea ice levels vary, so too do the overall long-term and year-to-year levels. And it's here that those previously discussed feedback mechanisms come into play.
There are several different feedback mechanisms that affect Arctic sea ice. The most predominant of these are the ice albedo feedback and the thickness growth feedback. And these kind of act against each other to some extent. The ice albedo feedback comes about because the ice and the snow have much higher reflectivity than the surrounding ocean. So as you melt sea ice, this exposes more of the darker ocean to the sun, which means that more of the sun's rays is absorbed, which leads in turn to increased melting.
So when we figure in feedback mechanisms, is it then reasonable to talk of tipping points in relation to sea ice? One potential tipping point is based on something known as the halocline.
The Arctic Ocean subsurface structure consists of a very cold, fresh layer of water, which is derived from ice melting and land runoff. And this sits on top of a relatively warm layer of water, which comes from the North Atlantic. The warm layer is currently prevented from reaching the near surface by the halocline, by this cold, fresh layer above. But the warm layer contains enough heat to melt all the sea ice many times over. So if it could be mixed up to the surface, then it would likely cause very rapid ice loss. And it could mean that the Arctic remains ice-free, even if global warming were to be reversed.
So, Tim, this is a really interesting system to me because the Arctic is clearly important for a whole bunch of reasons. The Arctic is important as a generator of weather impacts on other parts of the system. It's really important because it's sort of almost unique in its structure. It's dark during the winter and it's very light during the summer. There's all sorts of interesting things here. And what really interests me about this is that there are seemingly several tipping points here which are interrelated. Could you talk about the wider impacts in the Arctic?
The Arctic is the place where a sort of cascade of unwelcome tipping point changes may be starting, because it's clearly the place that's warming up 2 to 3 times as fast as the global average. So yes, on the one hand, that's contributing to the accelerating melt of the Greenland ice sheet, but in terms of the ecology, much amplified warming on the, say, Eurasian and Canadian and Alaskan land surfaces is contributing to thawing of the permafrost, release carbon to the atmosphere that only adds to the warming. And we're also seeing evidence of an increased fire regime in the boreal forests, and the soot that's coming from those fires, depending on which way the wind is blowing, can sometimes land on the remaining ice and snow, and that black soot, of course, absorbs the sunlight better than the snow and adds again to the melting. So lots of things interacting in the Arctic, and worryingly, they can then spread out potentially to the rest of the planet, because we know already that there's greater warmth and greater rainfall on the Arctic, and there's the melt of the Greenland ice sheet. And as Richard Wood mentioned, that extra fresh water is very likely to be contributing to that slowing down of the Amok that we talked about, that then connects all these changes out to the rest of the planet.
So you've got a deeply interconnected system there, and the feedbacks are acting on one another and they might cause further tipping points. You talked about a cascade.
In the worst case scenario, you'd have a cascade where tipping one thing made it inevitable that you tip the next. I don't think we're in quite as bad a situation as that, but clearly we have evidence that tipping one thing is increasing the probability of tipping the next. And that's certainly adding to the risk we're running here with these climate tipping points, because we really don't want to get into a situation where this escalates. And then you'd really just have to try and imagine if anyone's still around a few hundred years down the line, looking back on it, they would just see what started in one place cascaded out and would be defined as eventually a global tipping point with the benefit of hindsight.
You talk about an escalation of tipping points. As well as trying to understand the interaction between Earth systems, it's also important to consider how the rate of change within each system may affect our climate. Earlier this year, a team from Copenhagen, led by Johannes Lohmann and Peter Levson, set out to investigate exactly that. The focus of their research was increased levels of fresh water in the North Atlantic. Here's Johannes Lohmann.
So what normally is being done when studying tipping points is to look at a system in isolation. And typically what is being done is that this parameter is being changed very slowly. And then at some point you reach this critical threshold where the system can collapse because the state of the system just loses its stability. But this might not be so realistic for 2 reasons. First of all, climate change is unfolding at an accelerated pace. So this slow change of the parameter is not really so realistic as you go into the future. And second of all, if you have a change in the conditions of the climate that are not slow, it has been known from the mathematical community that there are other types of tipping points that could be at play here, where the system could actually tip before you reach such critical threshold. And this phenomenon is called rate-induced tipping.
So they're talking about rate-induced tipping. They're talking about the rate of melting. As you increase the rate of melting faster, that makes it more likely to tip the ocean circulation into this off state.
That's right, Doug. And actually, Thomas Stocker and Andreas Schmittner showed that back in the 1990s. And the same argument can apply to the permafrost, where maybe it's perhaps more intuitive to think about that the faster you warm things up there, the more you risk that you trigger a self-propelling process where you're thawing this organic carbon soil out of the deep freeze, and once it starts to thaw, the bugs start eating the carbon, and eating gives off heat in and of itself, so that adds further to the melting. So yeah, it's very ironic that in the earliest consideration of the United Nations Framework Convention on Climate Change, originally it was going to be included that the rate of climate change was something we needed to limit as well as the absolute amount. But somebody very early on in the 1990s concluded that would be too complicated for politicians to cope with, so they just reverted to having round number targets. Now we're busy reminding the world that the rate matters as well as the magnitude.
So one thing I'd really like to talk about finally is resilience and changing resilience. And I'd like to talk about another really important system further south, and that's the Amazon rainforest. You hear a lot about the Amazon rainforest because of wildfires and deforestation. And we've got a great interview here with Dr. Liana Anderson, who's a researcher at the National Center for Monitoring and Early Warning of Natural Disasters in Brazil.
The Amazon plays an important role in regulating Earth systems. This region is home to half of the world's tropical forest. Due to its extent, a large amount of carbon is stored in this forest. The Amazon forest is also responsible for regulating the hydrological cycle for much of South America. Every tree can be considered a water pump, which absorbs the rainfall, processes it, and emits large amounts of water vapor to the atmosphere. The trees emit other gases into the atmosphere, which are essential to cloud formation.
The Amazon has lost about 20% of its original forest, and from 2002 to 2019, more than 39 million hectares have been cut. That's 1.6 times the area of the UK. Forest clearance has manifested itself in a number of ways.
The annual average temperature in the Amazon is now approximately 2 degrees higher than at the beginning of last century, with documented impacts which includes longer dry season, record-breaking droughts and floods in the last 6 years, the reduction in evapotranspiration by the forests in southern Amazonia, and the decrease in the air moist transport.
So, Tim, we know that a huge amount of the Amazon has been cut down, and this impacts the forest in a number of ways.
So on a local scale, we see the forest is drying. For example, we get more fires, and fires tend to further destroy trees, which tends to further destroy the microclimate, promote grasses, which promote more fires. And that kind of can spread out locally. But also we have this incredible effect that the prevailing winds are blowing moist air in off the Atlantic into the basin. It's raining on the forest. The forest is then re-evaporating the rainfall back to the atmosphere. And this cycles round. If you start drying out the forest and you start losing the forest, you start breaking that rainwater recycling. And that presents a big threat on a larger scale to not being able to maintain forest further in on that track of wind. So you got these interacting reinforcing feedbacks from the local fires and the larger scale circulation, which are the big reasons why we are concerned about a possible Amazon tipping point.
I've heard estimates of a tipping point at about 30-40% of deforestation. We're part of the way out there already, or a 4-degree local change. Either of those things might cause a tipping point, and obviously they might interact. So how close might we be to that kind of tipping point?
Well, a couple of researchers have even said it's only going to take, 20-25% loss of the forest for a tipping point. Let's hope they're not right, because we're very close to that now. I think, honestly, it probably matters which bits of the forest you destroy. Some could cause the tipping point earlier than others, depending on where they sit in the rainfall recycling system and so on. But the risk is clear, so the course of action is clear, frankly. Yeah.
So I was going to say, so we've got an uncertain threshold that we're moving towards. So what are those courses of action? And I guess finally, I'd like to bring in maybe a more hopeful viewpoint. What are the tipping points that might be positive? What are the tipping points which might help and be a force for good?
Well, if we start in the Amazon, obviously it would be good to reverse the recent trend of increasing deforestation. But if we then step back to the global climate problem, we kind of all know what we need to do to minimize the risk of climate tipping points, and that is meet the goal of the Paris Agreement on climate change and limit global warming to well below 2 degrees centigrade, striving to limit it to 1.5 degrees above pre-industrial. The problem is that already requires a spectacular rate of technological and social change to decarbonise the global economy, way faster than it's happening now. And that's why I'm refocusing quite a lot of my efforts on identifying positive tipping points in society, in technology, in the relation of the two together and with ecology that can accelerate the rate of social change and economic change that we need. And the good news there is we've already seen evidence of these tipping points. We've seen an incredibly strong tipping point in the uptake of electric vehicles, where Norway has led the world. And in the UK, we can be rightly proud that we've shut down coal burning for power generation from 40% of our electricity in 2012 to pretty much zero today.
So it sounds like social systems are a lot of potential.
They do, Doug, and that's kind of actually well known. It's well known that, for example, in US cities, a transition from horse-drawn carriages to automobiles happened in about 10 years at the start of the 20th century. It's well known to all of us that one Swedish school child skipping school on a Friday and protesting in front of the Swedish Parliament turned into a mass movement of millions of us within a year. And those are classic examples of self-reinforcing positive feedbacks within society. And we need more of that if we're going to meet the Paris Agreement, and we need to find and trigger some good social tipping points to avoid the bad climate tipping points.
Well, Tim, that was a really interesting conversation. Thanks very much for being with us today. Our thanks to Professor Tim Lenton, and our thanks to all the scientists who were interviewed for this programme, and also to Annie Schultz, who helped prepare it. The producers were Claire Nazir and Graham Madge, and the editor was Adrian Holloway. See you next time.
Mostly Climate is a podcast by the UK Met Office.